Welcome back to the course entitled Symmetry, Stereochemistry and Applications. In the last lecture, we have discussed about the possibilities of different two-dimensional space lattices. And before going to the next topic, I would like to quickly discuss about a problem which I gave you in the first lecture. I asked you to find out why tetragonal face-centered lattice is not a different lattice, rather it is something else. And maybe some of you have found out, and some of you have not found it out. So for all the students, I would like to draw the tetragonal F lattice and discuss why tetragonal F lattice is not one of the Bravais lattices. So to demonstrate that, I first need to draw nicely a tetragonal lattice and then convert it into a tetragonal face-centered lattice, and from there we can start. So this is a tetragonal lattice, and when I say it is face-centered, it essentially means I have objects at all the faces, all the corners, and center of all the faces. So this is a face-centered tetragonal lattice. Just to address the problem that a face-centered tetragonal lattice does not exist, we extend this tetragonal face-centered lattice in the next unit cell. So what I am trying to draw is I am trying to draw two tetragonal face-centered lattices side by side. These are two tetragonal face-centered lattices drawn side by side. Now, if I try to redraw this unit cell using green color slightly differently, now, if I ask you what is the area of the original tetragonal, volume of the original tetragonal lattice, you would say that it is A into C is A square C. That is the volume of the original tetragonal unit cell. What is the volume of the modified tetragonal unit cell with green color? The edge length is nothing but root 2a. So it should be root 2a square into C. That means it should be root 2a by 2, that is a by root 2. So the volume of that unit cell should be a by root 2 square into C. That means half a square C. So the green tetragonal lattice has a smaller volume compared to the yellow lattice. That means we should consider the smaller volume as a repeating unit, not at the bigger volume. And then when we look at the smaller volume tetragonal lattice, which is green one, you have atoms at 8 corners, and the face center atom which was there is now the body center atom of this tetragonal unit cell. So this is a tetragonal I lattice, not a tetragonal F lattice. The F lattice has a double volume compared to the I lattice, and therefore we should consider this as I lattice and not as an F lattice. So this is why we don't have a tetragonal face-centered lattice as one of the Bravais lattices. Now let us try to see what are three-dimensional crystallographic point groups. See, these point groups that are there in three dimension are formed by the n-fold axis, where n is equal to 1, 2, 3, 4 and 6, with the n-bar axis, where again n equal to 1, 2, 3, 4 and 6, and in combination with those you will have mirror planes. So these symmetry elements will give rise to 32 point groups. A full list of point groups can be found in any textbook. For example, F.A. Cotton's book that I have been referring to in chapter 11. So the most unsymmetrical point group is 1. That means no symmetry. There is no symmetry in the unit cell other than a 360-degree rotational symmetry. The second symmetric point group should be 1 bar, which means it has inversion symmetry. So a molecule and its inverted object is present in the unit cell. The next possible higher symmetry could be 2, is written as 2, that is, it has only two-fold axis of rotation. The next point group can be 2 bar. Then you can have 3 and 3 bar. Then one can have 3 bar associated with M. There can be 3 associated with M, and so on, with threefold symmetry. And the higher point groups can be like 4 bar, 4 by M, 4 by M, 4 bar 2M belonging to tetragonal systems, and then you can have M, 2, 2, 2 or M2 for orthorhombic systems, and some space point groups like 3, 2, M3 bar M, etc. for cubic systems. So like that, there will be total 32 different point groups identifying different crystal systems. Say for example, these are for triclinic, 2 bar, 2 by M, only M. These are for monoclinic. These are for trigonal or rhombohedral. These for tetragonal. These for orthorhombic. And some for cubic. And of course, if you have 6 by M, 6 by M, for hexagonal systems. So these 32 point groups can be divided among in terms of center of inversion. If you have inversion symmetry, then we call it as centrosymmetric. I is present. And the other one is non-centrosymmetric. That means inversion symmetry absent. And then in this non-centrosymmetric point groups, there can be two different types, chiral and achiral. Chiral means mirror is absent, and achiral means mirror is present. So when we try to identify these point groups in terms of center of inversion, for centrosymmetric point groups, we can write as 1 bar, 2 by m, m, 4 by m, 4 by m. These things are centrosymmetric because these point groups contain an inversion center. So what you will see that if you do the higher level crystallography course, there you will get to see that when you apply 3 mirrors, it will immediately give rise to the inversion center. When you have a twofold axis and a mirror perpendicular to that twofold axis, that gives rise to a center of inversion. So when we write this 2 by m, means you have a twofold axis and the mirror plane is perpendicular to that twofold axis, which is equivalent to, suppose in molecular symmetry, C2, and a plane which is perpendicular to your C2 is written as H. So it is equivalent to have a C2H point group in molecular symmetry. So this is 2 by m in crystallography. When you say MMM, that means you have one mirror like this, you have one mirror like that, and you have a third mirror like this. 3 mirrors, when they intersect at one point, that point becomes the inversion center. So these point groups which I have written here are centrosymmetric because they have inversion center. The point groups which I am writing here, for example, I, 2, M, 3, 3m, all these, they belong to non-centrosymmetric space groups because they don't have center of inversion. So here, these point groups that you have, which are non-centrosymmetric, among them, some of them which do not have a mirror is called the chiral point groups, and that chiral point group can be 1, 2, 3, these things. On the other hand, the point groups which are containing mirror like M, 3m, MM2, etc. These are called the achiral point groups but non-centrosymmetric, and they are called the achiral point groups. And in case of chiral, one can also write 2, 2, 2, etc. So the point groups can have chirality, and a chiral compound will always try to go and crystallize in chiral point group, and eventually they will be crystallized in chiral space groups. So now one may be asking, what do we mean by space group? As I indicated in one of my earlier classes, that when you combine the Bravais lattice information with the symmetry of the lattice, that means the point group, and the additional symmetries that may be present, like screw axis and glide planes, then what we get is a representation called the space group. So this space group is again restricted in number. As you can see, there are 230 space groups, and these space groups represent all the 7 different crystal systems and have different Bravais lattice information. So these space groups are written like this. This simplest one is P1, which means it is primitive and no symmetry. That means there is no symmetry element and it belongs to point group 1. P1 bar means primitive plus I. The next point group, the space group one can think of is P2. So it is primitive plus have a two-fold axis. One can have P21, which means primitive, plus a 2-1 screw axis. Similarly, P2 by M means primitive plus two-fold plus perpendicular mirror. Similarly, PM would mean primitive plus M symmetry, mirror symmetry. So if you write C2, now it means a C-centered lattice and a two-fold axis of symmetry. So like this, one can continue and write 232 different possibilities for space groups. So in this case, we now have gone beyond the concept of point group, because the point group is related to the molecular symmetry, and then the point group is related to the symmetry elements that are present in the unit cell without considering the translational symmetry elements like the glide planes and the screw axis. So these space groups can also be centric and non-centrosymmetric. Centrosymmetric means contains inversion symmetry, contains I in it. Non-centric means no I, that is, there is no inversion symmetry present in the lattice. This non-centrosymmetric once again can be subdivided as chiral and achiral. So when we say that centrosymmetric, it contains I, one can identify some point groups here, P1 bar, P2 by M, C2 by M, P21 by M, PMMM, PBCA, P4 by M, P4 by M. All these which has the inversion symmetry are called the centrosymmetric point groups. Non-centrosymmetric point groups can be P1, P2, PM, PC, C2, CM, P212121, PMM2, P4, P41, many such combinations. So now when we talk about the chiral point group, space groups, chiral space group are those non-centrosymmetric space groups which do not have a mirror symmetry. And achiral space groups are those non-centrosymmetric which can have mirror symmetry. So achiral belongs to non-centric but can have mirror plane, and chiral do not have a mirror plane. So examples are P1, P2, C2, P21, P4, P41, P2121, P222. These are different chiral space groups, whereas PM, PC, CM, PMM2, PCA21, PNA21, these are non-centrosymmetric but achiral space groups. So when we try to crystallize a compound and then we know that the compound is a chiral molecule, then we will end up getting one of these space groups which belong to chiral. I'm just giving you some examples of chiral space groups. It is not only limited to these space groups which I have indicated here. Rather, it has a large number of space groups which belong to chiral, a large number belongs to achiral, and a certain number belongs to a centric space group. Altogether, there are 230 space groups that are possible. So with this, I'd like to conclude this course saying that the symmetry elements that we have learned in the beginning of this course for molecular symmetry can also be extended and then the knowledge can be used to understand the crystallographic symmetry. And one thing that one should always remember, that the molecular symmetry that you have learned has the symmetry elements contain the object. That means the symmetry elements always pass through the object. Whereas in case of crystallographic symmetry, the symmetry elements are in general outside the object, and those symmetry elements relate the two objects located in space. And in certain cases where the symmetry element of the object is matching with the symmetry of the lattice and they are coincident, then you get the molecule only represented as half or 1/3 or 1/4, whatever the case may be. So I hope you have enjoyed the course, and I do not want to extend this discussion on crystallographic symmetry because it is beyond the scope of this course. And those who may be interested to learn more about crystallographic symmetry and X-ray diffraction, I have offered a different course dedicated for X-ray crystallography. So those may attend that particular course called chemical crystallography, and that is generally offered in the August semester. So I hope you have enjoyed the course. If you have any problems, you have doubts and questions, please drop email to me. I will be happy to answer. And I wish all of you a very happy year ahead, and I wish you all the best for your final exam. Thank you.